Another famous example of interference by reflection is the so-called Newton's rings. This is none other than the great Sir Isaac Newton himself. So he followed us all the way from 1A through 1B, now to 1C. Okay, Newton's rings. What is a Newton's ring? Well, it is an interference pattern set up by something like this. You have a flat piece of glass, okay, and then you have another piece of glass with a spherical shape, spherical surface like this. Here, the glass is pretty thick. Okay, the thickness here is way greater than what would allow interference to occur. So do not expect any interference from a beam here and from a beam there because it's too thick. Okay, this is too thick. However, if you make the radius very large, then this piece is nearly flat, and this, of course, is a completely flat piece. So therefore, there is an air gap between this curved surface and this flat surface. This air gap can be pretty narrow. Okay, again, because this is also nearly flat. Now, so let's say the center of this sphere, of this spherical surface, is right here. Okay, and we call it this O prime. Now, the radius is r. Right? We can calculate the thickness here, depending on the distance between the central axis and that point, small r. Okay, we can easily calculate that. And suppose we have a certain thickness here, and then suppose we consider a beam of light. Okay, a beam of light coming in. It gets reflected off of this surface, and the same beam can go into the air gap and gets reflected again. Okay, so here's a second reflection. So one gets reflected here, another one gets reflected there. Now this air gap T can be narrow enough so that these two beams can be coherent. Okay, these two beams can be coherent. So are you going to get a bright spot here, a dark spot there? Okay, let's see here. You get a bright spot if these two beams are interfered constructively, which means without any pi fish consideration, the path difference between them would be equal to n lambda. Okay, the pi's difference is we know it's equal to 2t, right? Because the second beam travels an extra distance 2t. T go in, t go out. So 2t equals m lambda. This is an air gap. N is roughly equal to 1, the index refraction, so I'm not going to divide it by n anymore. Okay, m is just an integer. Okay, just an integer. Actually, it's a natural number, 1, 2, 3, 4, and so on. Now, is there a pi phase shift? Well, look at this here. This is glass and this air. So there's a pi phase shift here for beam number 1. What about beam number 2? Beam number 2 gets reflected from the air, off of the glass back into the air. So there is no pi phase shift for the second beam. So there is indeed a net pi phase shift between these two beams. Therefore, this condition is the condition for minimum. Okay, not for maximum. So that's minimum. And m plus 1/2 lambda. That is maximum. Okay. Now, imagine as you go out, t will increase, right? T will increase. And whenever t satisfies this condition, for m equal to 0, 1, 2, 3, whatever, whenever a condition like that is satisfied, you're going to see a bright spot. Or, more precisely, because this is a cylindrically symmetrical setup, you're going to see a bright ring. Okay, you're going to see a bright ring. So, you're going to see ring-shaped structures like this as you go out. These are called Newton's rings. Okay, these are called Newton's rings. Now, what about the point right in the middle? Well, the point right in the middle should be a dark spot. Why? Because it satisfies this condition, right? T equals 0, right? There is no thickness. And the reason why with T equal to 0 they have a dark spot is because one of the beams has a pi phase shift, that's number 1, and number 2 does not have a pi phase shift. Okay, so that's why the middle of the Newton's ring pattern is a dark spot. Okay, now, if this is a completely symmetrical setup, so that you have a uniformly increasing, so this is basically the curvature here and the curvature there exactly balanced, then you are going to see totally concentric circles, right? Totally concentric circles. Now, the way I draw it, however, is not quite concentric. In fact, let me exaggerate this a little bit. If I draw something like that. What does that tell you? Well, along every ring, T is a constant, right? Because T has to satisfy this condition. T is a constant. So the difference here is here, as you go a little bit, T changes a lot. Here you have to go that far for T to change by the same amount. Okay? What does that tell you? It tells you on this side, the thickness, the air gap does not grow very fast. And on that side, the thickness grows faster. Okay? So if I were to exaggerate this, then I would get something like this. Okay? You see here it grows, the thickness grows pretty fast. Here it grows slower. Okay? And then what that tells you is that by looking at interference rings, you can determine whether, whether this shape is really spherical or not. You can detect any imperfection in the geometrical contour. Right? This is an excellent way of detecting minute imperfections in geometrical patterns using interference. Okay, and we use that a lot in industrial applications. And we can easily calculate the radius of Newton's ring, assuming it's perfectly concentric circles. We can actually find out r. Okay, r can be a function of t and radius. Let's do that. Okay, from here to there, that's one radius, right? And then what about from here to there? Now that would be r minus, okay, right angle triangle, right? Will be r squared minus small r squared. R squared minus small r squared, and then take the square root, right? That takes you from here to there, right? And then you take the whole r minus that, that's t, right? That's t. Now from here you can find what r is corresponding to a certain thickness t, right? This r, once again, is the radius of Newton's ring, the radius, right? The radius. So this is how you can find it, and I'm not going to finish the algebra with you, but in principle, that's how you can do it. And again, if the Newton's rings are not perfectly concentric circles, that tells you, the shape here is not exactly symmetrical. Okay, some even more examples of interference. Suppose I have a thin film. It's not exactly even in thickness. Rather, it's shaped like a wedge, which means the thickness grows linearly. Okay, from t to t prime and further and further. It's a straight line here, straight line there. Now, suppose then you have a beam of monochromatic light shining upon it. Monochromatic light. What are we going to see? Well, we know when the thickness satisfies certain values, you're going to get a bright reflection, right? And then it's not a single value. There is a integer m in it, right? So here, let's say this is m equal to 0. You're going to get a bright reflection right here. Next one, m equals 1 is here. Next one, m equals 2 here, and equal to 3, and so on. And because the thickness grows linearly, the spacing between adjacent maxima will also be uniform. Okay, so what you get is interference fringes. Okay, you just get bright fringes like this: red, 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 red. They are evenly spaced. Okay, and what if the incoming beam of light is multiple colored? Let's say sunlight. Then what you're going to get is that you have multiple sets of maxima. Here is the maxima for red. Okay, and the next one is for yellow. So here's yellow, 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 and then other colors such as green. And that's what you're going to see. Okay, and the spacing is quite even. All right, the spacing is quite even. You can see all kinds of colors repeating its pattern. Now, another example would be an air gap. So you have here some materials of whatever thickness, another some material of whatever thickness, but in between them there is a wedge, a very narrow wedge of air, or air gap. Okay, then you can imagine a beam of light getting reflected like this, another beam of light getting reflected like that, and when they satisfy the right interference condition, they can have a minimum, a maximum upon reflection. This is in fact just like Newton's ring, except in this case, because this is straight and that is straight, the the thickness T grows uniformly, and therefore you are going to get evenly spaced. Okay, you're going to get evenly spaced rings or fringes like that. Okay. Unlike Newton's ring, in Newton's ring, the diameter of the ring does not grow uniformly. Okay, it grows faster and faster and faster as you go away from it, and the reason is because it does. It's not a straight line. Okay, the thickness increases non-uniformly. It increases faster and faster and faster, and therefore the rings will get closer and closer and closer to each other as you go out. Okay, the rings are getting closer and closer and closer to each other. Okay. Now, a last example. What about soap bubbles? Okay, soap bubbles under the illumination of the sun would appear to be multiple colored, and this in fact is a matter of thin film interference. A soap bubble has non-uniform thickness, and it's also being illuminated with multicolored sunlight. And then in a certain direction, okay, we look at it from this direction, you find the thickness is such that the red color is enhanced because of constructive interference, so this appears to be red. And at the next location, at this location, the thickness is such that the yellow color will be enhanced, so it appears yellow. And and another location, it turns out the green color is enhanced. That's why you see multiple colors coming out of it. Okay, so it's a matter of which color undergoes constructive interference at whatever angle and whatever thickness. Okay, so you see. Interference really is everywhere. They appear in our daily lives. If you pay attention, you're going to see them. Okay, let's look at one last example of this chapter. Okay, this time we are going to revisit Young's double slit experiment, but we're going to add a little twist to it. You have two slits, S1 and S2, separated by distance d. I'm looking at an angle theta away from this reference line. Okay, I'm looking for an interference pattern as a function of theta. Now the twist I add here is that I'm going to introduce a slab of glass of thickness T, okay, not very thin, or not very thick, okay, and this slab of glass has index refraction of n. Now my question is, when you introduce this slab of glass, what happens to the interference pattern? Okay, what happened to the interference pattern? Well, it turns out, if you do the experiment, you'll find the interference pattern will be shifted, okay, the whole pattern will move along the screen. Why is that? Okay, we can understand why by looking at the idea of a phase difference. The reason why you have a constructive interference is because these two beams are in phase. Okay, in particular, in the middle of the screen. Okay, without this piece, in the middle of the screen, this beam and that beam will have exactly the same phase. Okay, so the phase difference is zero. Okay, it's zero. Now, as you insert this glass slab, the midpoint of the screen, where theta equals 0, no longer has a phase difference of 0, right? Because you insert a piece here, even if theta equals 0, okay? So they travel the same distance, right? This path, when you have a glass slab inserted, it's going to shorten the wavelengths for the wave traveling inside of it, right? So even if it travels the same distance t, it's going to spend more number of wavelengths. With every wavelength, you are going to have a 2 pi phase difference. Okay, so by the time they arrive at the center of the screen, the first wave will have traveled more number of wavelengths than that wave. Okay, so its phase is going to lead against that. Okay, so my question is, where is the new location where the phase difference between these two waves is exactly 0? Well, again, the first beam, the first wave will have greater number of wavelengths traversed because it enters this region. To compensate for that, I want to look at a certain direction away from theta equal to 0 so that the second beam travels a further distance in air. That distance, delta x. Okay? So that the second beam also spends a few extra wavelengths because it travels an extra distance. When these two effects cancel out, okay, in other words, if, for example, the first beam travels an extra 5 wavelengths because of shortened wavelengths inside, but the second beam also travels an extra 5 wavelengths because it spends more, longer distance in air, then their phase difference will still end up 0, right? So let me look for the angle theta naught, such that along that angle, the two waves will have exactly the same phase. That will again be the center of the interference pattern. Okay, the center of the interference pattern. So what I'm looking for is this. I'm looking for a cancellation between the added phase here and an added phase there. Okay, what is the added phase here? Well, without the wave, without this glass slab, how many wavelengths would it travel? It would travel this wavelengths of T over lambda, right? T over lambda inside. Okay, and the phase difference would then be T over lambda. Here, lambda is the wavelength in vacuum. T over lambda, that's the extra number of wavelengths traveled, and with each wavelength traveled, the phase difference is 2 pi. Okay, that is without the without this glass slab. Now, with the glass slab, the wavelength is now shorter than before. Is now shorter than before. How much is lambda over n? Right? So, with the wavelengths, how many extra wavelengths? How many wavelengths is what it travel to go from here to there? That will be 2 pi t over lambda divided by n, right? That's the new wavelengths, right? New wavelengths. So, what is the difference in the number of wavelengths spent when you insert the glass slab versus the case without the glass slab? That would be t divided by new wavelengths minus t divided by the old wavelengths, right? And that is the additional number of wavelengths traversed by the first wave due to the insertion of this glass slab. Okay? And you take that difference times 2 pi, you get what? You get what? You get the extra phase angle caused by the insertion of this glass slab. Okay? And that's right here. And that has to cancel with the extra phase difference due to the fact that the second wave travels a little bit longer than the first wave. Okay, so what does that equal to? It travels an extra distance of d sine theta. D sine theta. Right? D sine theta. You multiply this by k. Right? K is 2 pi over lambda. What do you get? You get an extra phase angle caused by the fact that the second beam travels an extra distance delta x with the wavelength lambda. And when these two effects cancel, so I make these two phase differences the same, then when these two waves arrive at a certain location on the screen, they will still have the exact same phase difference, whereas the phase difference between them is 0. This is the angle I'm looking for. Okay, we can simplify the calculation now by crossing out lambda. There's lambda, there's lambda, there is lambda. Crossing out 2 pi, then I get and flip n over, so I get n minus 1 t. Okay, right? N minus 1 times t equals d sine theta naught. This is the new angle theta naught that will be aimed at the center of the diffraction of the interference pattern. So initially the interference pattern is centered right here when theta equals 0. The new center of interference pattern will now be there. Theta naught. This is the new center. So there is a shifting if you insert the glass slab. You see the entire front shifting from here to there. And that is how we determine this angle theta naught. Okay, so this is another example just to illustrate how we might change the phase of a wave by inserting a piece of glass slab. Okay, you can also shift this pattern with another way, and that is you can assume a beam of light is not incident upon it normally, but rather at an angle. Okay, so at an angle like this. So the wavefront is like that, right? Okay, now if you consider this case, I'm not going to finish the algebra, but I will leave that as an exercise to you. Look at beam number 1 and beam number 2. When the wavefront, when this wavefront has arrived at the second source. It has not yet arrived at the first source. You see here? It is to travel an extra distance before arriving at the first source. So when these two, so the wave coming from here, coming from there, will no longer have the same initial phase. You have to take that into consideration. Okay, so if you compare these two waves, even though the second wave traveled an extra distance, this much, after going through the screen, after going through the slits, the first wave travels extra distance of that much from here to there before reaching the slits. Okay, so that's something you have to consider. Of course, along that line, that's the same wavefront, they have the same phase. Okay, so you use that as a reference line. The first wave travels extra distance that much, the second wave travels extra distance that much. Okay, so it is the difference between this lens and that lens that's responsible for the phase difference of these two waves arriving at the screen. And if this lens equals that lens, then what? Then without this glass lamp, these two waves will be completely in phase, will have the phase difference of 0 upon reaching the screen. And that will be the new value of theta naught. Okay, so that's another way to shift the pattern on the screen. In the next chapter, we are going to look at how we might consider adding these waves together when the source is no longer numerable like 1, 2, 3, 4, 5, rather it's a continuous source. That, of course, calls for the idea of diffraction.